and then went to Zurich, then Heidelberg, where Andrea was became a group leader, which I think is sort of like an associate professor. And then he's been in NYU-AD in the physics department there for 3.5 years now.
Yes, correct.
So Andrea's work, well, he'll describe it better than I can, but roughly speaking, it's to simulate how galaxies form. And of course, this is a very important problem because it appears that there's some form of matter, dark matter, which is, say, 4 or 5 times more abundant than ordinary matter. And historically, since dark matter is believed to only interact gravitationally, the simulations or studies of dark matter involved, of galaxy formation involved just dark matter with just gravitational interactions, ignoring ordinary matter. And there were a number of anomalies, things that didn't seem to work, that when you observe galaxies didn't match the results of these simulations. And so I guess most of Andrea's work, at least recently, has been adding in the physics of baryons, the physics of visible matter, to see how that affects the structure of galaxies, and that makes many of these anomalies either disappear or at least recede in significance. So I think that will be the main topic, and great to have you.
Thank you.
Yeah.
Well, thank you everyone for being here on a Friday afternoon. I appreciate it. And my idea of this talk is to tell you why galaxies are important and why to study galaxy formation. So that's my first thing. Why galaxy formation? Well, galaxies are amazingly interesting objects. They are the cradle for star formation. This is the antenna galaxies, and that's where most of the stars are forming as the 2 colliding galaxies. Galaxies are also very interesting because they shine practically through the whole electromagnetic spectrum. It's the same galaxies seen from the radio down to the X-ray. Galaxies are also very interesting dynamics objects. I thought Scott Tremaine was here, so I decided to put his book. This is 2 interacting galaxies. The galaxies are dynamically extremely interesting objects. And also, galaxies are the places where we have the most energetic phenomena in the universe. What you see here is radio galaxies, and this is a radio jet. I mean, this is the size of the galaxy, that's the extension of the jets, which is like 10, 15 times larger than the galaxies. So galaxies are very extremely interesting objects, but actually, none of those is the reason why I study galaxies. So I want to tell you why I study galaxies. To do that, I have to make a step back and tell you about the content of the universe. So we know nowadays pretty well that the universe is mainly dark, and this is the matter energy density of the universe, and roughly 70% of the universe is in dark energy. We don't know what dark energy is, but we know that it runs the accelerated expansion of the universe today. Then when it comes to the matter, 80% of the matter sector is actually in dark matter, as Matter was saying before. We know that this matter does not couple with electromagnetic radiation. Most likely it doesn't couple neither with the strong or the weak force, and it's only interact with the ordinary matter through gravitation. And then we, atoms, we are only this 5% of matter. And the main assumption for dark matter is that dark matter is cold. That's why I usually talk about cold dark matter. What it means is that it doesn't have much of the velocity at the coupling, so it's created practically at rest. It means that all the velocity that dark matter has is usually due to the gravitational potential. It's dark in the sense it doesn't interact with the gravitational, with the electromagnetic sector, and it has this collisionless, so it's a negligible cross section. That's the main assumption for the cold dark matter model. Okay. Now, it's true that we live in a very specific, precise time, the price of precision cosmology. So we know most of the parameters that we were describing before. This is the dark energy density of the universe, that's the matter density of the universe, that's the Hubble constant, with the exquisite precision. That's from the Planck satellite. And so practically we know that omega matter is 3.104, and look at the decimal numbers here. And this is not something that was true a few years ago, because if you only go back 20 years, that's a paper by Matthias Barteman.
Some people may not know what omegas are, so.
Oh yes, sorry. Omega, this is simply the fraction of the total energy density which is in dark energy. If you go back to this pie chart, this is the total energy density, 68.3% is in dark energy, and then you can try, omega is simply the ratio of this, the ratio of this number with respect to 1. So it's practically telling you how much of this dark energy, the energy density of the universe is in dark energy, and this one is the one which is in matter, which is maybe dark. So probably if you sum up these 2 numbers, you should get 1, which is the total matter density of the universe.
You have to update your pie chart percentages.
Hmm?
You have to update the percentages.
Yes. I know this. So I think it's 1W7. This one I grabbed it this morning, and it's very different. This is not what was there. I mean, 20 years ago, we didn't have much of an idea of what was happening. In fact, in this paper, this is a paper by Matthias Martman, and he was trying to do some simulations, and in order to cover all possible spectra of the cosmological model, he had to run huge amount of simulations. So you see, he had some simulation where the total energy was 1, so everything was in matter, and there was no dark energy. He had models which is 0.3, 0.7, which is very similar to what we had today. It also had models when all there was only 0.3% in matter, nothing in dark energy, and the remaining was in curvature. So we thought the universe was not flat, but it has some curvature. So practically we went from not knowing if those numbers was of the order 1 or 0 to an extremely high precision. But I'm going to argue that this is more than precision cosmology. This is something like precision measure of our ignorance. Because what those numbers tell you is that we know exactly nothing, more or less, about 68.96% of the content of the universe. Because as today, we don't have much of an idea what dark energy is. And the same goes for dark matter. What we know is that practically if you remove the 5%, which is the ordinary matter, the one which follows the standard model, we know roughly nothing about 26% of the content of the universe. So our knowledge of what dark matter is the same as 1998. So in the last 20 years, we've been able to go from not knowing whether there was 30% of dark matter in the universe or 100% of dark matter in the universe to a very precise measurement. But what dark matter is, we are back in 1998. We haven't proceeded much. And now this is not because people were not looking for dark matter. In fact, there is a huge industry of particle physicists and particle physics experiments trying to look for what dark matter is. This is a typical plot that is usually shown by particle physicists. You have here the mass of your possible dark matter candidate. That's for a WIMP. WIMP stands for Weakly Interactive Massive Particle. It's maybe the simplest model of dark matter that we have nowadays. And this has to do with the supersymmetry and the extension of the standard model. And now what people do in this kind of experiments, they have the mass of the candidate, which is GeV over c squared, and they have some cross-section with nucleons. So these experiments, mainly what you have is you have huge tanks, usually of some inert gas, for example, xenon, and you hope that one dark matter particle, xenon is also almost kept at 0 temperature, and you hope that one dark matter particle is going to hit one of the xenon nucleons, giving it some kinetic energy, and this energy will be then transformed into electromagnetic radiation, usually through photons and electrons, and then you can detect this. Okay? So what you have here are mainly exclusion plots, because we haven't detected any dark matter so far. So the way to read this plot is that whatever is above those lines, this is, for example, from xenon, this is an older plot, I have a better one in a second, up to 2012, so whatever is above this line is excluded. And whatever is below this line, it's available. Now, one can think that one can keep doing this game if dark matter is indeed a WIMP, for some reasons, because nature is being kind to us. By pushing down this line, sooner or later we're going to detect it. Maybe the true dark matter is down here. It's 110 to the minus 47 in some units for cross-section. The problem is that if you keep doing this game, you're going to hit the floor. And the floor is given by this line here. And what happens is that you're going to become so sensitive to your experiments that you're going to start detecting neutrinos. So practically, we know neutrinos are a very small cross-section for interaction with ordinary matter, but it's non-zero. And the point is that if you keep pushing down your experiment in the sensitivity, you're going to hit this floor. And then your background is going to become the neutrinos. So you're going to start detecting neutrinos. And this is kind of a game over, because as we all know, there's no way to screen neutrinos.
No, but
right?
you know information about directions and so on. So it's
you have
it's
some
kind
information
of,
about direction, but most of these experiments are not being built with
right,
information
not so
about
far,
direction.
but
Not
I
so
mean,
far.
to say that it's ground over is, I don't think.
Yeah, so this is the situation right now, which is it's not game over, but for this kind of experiments, when you have practically non-directionality and you have big tanks.
Of course, I'm just saying,
Yeah.
I think you're really being unfair when you say we know nothing about dark matter. Those guys worked really hard and made amazing advances
It's true. But
in how weakly, you know, how, so a huge amount is
I agree with that, but
I
this,
agree
we
positively
know
we don't
we
know.
know what dark matter is not, but we haven't made any.
But that's a lot of progress.
Yeah, but practically this axis here, which is the mass, this is just one piece which is one which can be explored. There is no actual limit on the right and no actual limit on the left, because you can make your dark matter extremely low matter. So practically, you're trying to carve out space on a parameter space which is very, very huge.
Right.
Yeah, no, I mean, I'm not saying this is not a good game. I'm just saying that it's a game which is this kind of direct detection of dark matter is soon going to be arrive to an end. And this is the latest thing I could find for the particle data group. And you have here, this is the region which practically it's prevented by neutrino scattering.
It's just
So-
what's happening is people are now getting more imaginative and figuring out how to look in other domains. So it's not like the subject is ending. If
No, no, not at all,
anything,
not at
more
all.
people working on
But
it.
what people had in
I
mind,
know, I just,
yeah, I think what people hope
You
was
shouldn't
that this was.
exaggerate
I mean,
the
I've been to
lack of
conferences
particle.
and when I see people betting a bottle of champagne that dark matter is going to be discovered in 5 years. And that was maybe 20 years ago. And then every 5 years was, dark matter is there, and it's almost there, and it's almost there. And they didn't reach it. And now, as I say, that this kind of experiments, they're going to hit this floor. So, yeah, and dark matter could be, for example, a warm dark matter candidate, which I like very much, and it's
No,
going
no,
to be.
I don't mean to distract you.
Yeah,
I
no,
just think
it's-
it's not.
Fair enough.
Everybody who knows about it understands you're being
Yeah.
hyperbolic, but the rest may actually take you seriously, and that would be a shame.
Well, I
because-
mean, my point.
because the point is that people have explored very
My point is
thoroughly
that,
of
yeah,
theoretical prejudice.
this is
which
one of the
looking
best.
Wrong.
I agree.
And
This is one of the
then
best
there's
experiments
other
seen on
ones.
1 ton, and you see it's down there. Now
It
the
may not
thing
even
is,
be in that mass range.
yeah, correct.
But anyway, go ahead to your point.
Yeah.
which is,
So my point was that in this kind of games, sooner we are gonna hit the floor, and then we have to find some other way to try to understand what dark matter is. And then my idea is that we can revert to galaxies, because at the end, if you think about galaxies, galaxies are at the end product of the mix of the convolution of two things. You have one part which is the dark sector, the properties of dark matter and dark energy, and the other part is the galaxy formation. So galaxy formation, what I mean with galaxy formation, everything which is related to baryons, which means to gas, stars, and possible feedback. And now the idea is that if I can understand the galaxy formation part, and then I can observe galaxies, I can kind of reverse engineering the thing and try to learn something about dark matter. And that's why I study galaxies. So I've never been interested myself in galaxies per se. For me, galaxies are a tool to try to understand something on the dark sector, the part that we know nothing about, and that's the part that makes me uncomfortable somehow, that we know nothing about 95% of our universe. So the idea is that how can you do that? How can you relate the galaxy formation, study galaxies, and invert and everything go to the dark sector? Well, the method I use, and which the method you need to use, is cosmological numerical simulation. So when I was here in April, I gave a seminar talk, and I tried to explain why we have to use numerical simulations. And the reason is that in cosmology, we know the initial condition of our system, which is given by the cosmic ray background. So we know that at the redshift of 1,000, that means 300,000 years after the Big Bang, there was a tiny fluctuation of the order 10 to the minus 5 in our universe. Now, this fluctuation got amplified by gravity down to today, and today this fluctuation can give rise to galaxies. And that means this fluctuation I have to grow order of 11 orders of magnitude in order to create galaxies. So if you have fluctuation, delta over rho, which is 10 to the minus 5, you want to grow into a galaxy, this thing has to grow by 11 orders of magnitude. And I have an example, I had the ant, which grows by 11 orders of magnitude in mass, and I asked, what do you get at the end? And someone said 10 to 11 ants, which was a very smart answer. So from that point on, I decided to remove this kind of joke from my talk. And oh, by the way, if you take the mass of an ant and you grow by 11 orders of magnitude, you get 10 Airbus A380, the biggest airplane you have had. That's how much the universe grows. But it is that this is a highly nonlinear problem, and that's why you need to go use numerical simulations to use it. So you have to go into the numerical regime to solve the problem of galaxy formation. And what you need to do is to use what we call cosmological simulations. What does it mean, cosmological? Well, the idea is that you have to follow at the same time the formation of the dark matter, the gas, and the stars. So what you have in this movie is the following thing. I mean, rewind the movie. You have tiny density perturbation. This is just the dark matter view of a galaxy. This is dark matter density. And what you see from the beginning is that at the beginning the thing is kind of black because you have very tiny fluctuations. They get amplified by gravity. And then you see that the matter starts to collapse in this specific object here. This thing has the mass of practically our Milky Way. And this object here keeps creating other objects around. Okay, so that's the dark matter view. So if we had the possibility to have dark matter goggles, that's how a galaxy would look like in the sky. It's kind of ball of matter, which is denser in the center and less dense in the outskirts. Now, on the right panel, you have the gas. What the gas does at the beginning just follows the dark matter. So you see, if you have ball of dark matter, you have a ball of gas. What happens? The dark matter is it's tracking the gas into the potential well. But then things go slightly different, because the main difference between dark matter and gas is the gas can dissipate energy. Okay, dark matter cannot dissipate energy. Dark matter, the only thing it can do is to transform its potential energy and kinetic energy back and forward. Where the gas can dissipate energy, so it can release energy from the system as a matter of photons. And what you see is that the gas then becomes cold, and when it's very cold, which is blue in this plot, blue means cold, red means hot, star formation begins. So in this latest plot here, what you have is the stars. So at the beginning there are no stars, but as soon as the gas starts to condense in the center, it will start to transform part of its mass into stars. And that's what a cosmological simulation is. So it has the cosmological view that comes from the dark matter. It has the gas physics and has the star formation. So if I let this is the clock, the total life of the universe today is 13.7 gigayears. So that's how the galaxy proceeds through time. So there are merger events. You see, for example, this little satellite. There's another one coming here, which you see here in its gas, in its stars, and in its dark matter up there. And this is called a hierarchical assembly. It means that you see the object is keep accreting mass during its life. And then what happens is that while the dark matter stays like a ball shape, the gas is dissipating energy, but of course conserving angular momentum. There's another galaxy coming in. There's gas, stars, and dark matter. The gas is conserving its angular momentum, so it tends to set in a disk, and we got lucky in the specific simulation since we point the camera such that the disk is exactly edge-on in this specific projection. So that's how you form a galaxy in a cosmological framework. So the idea is that, come on. Yeah. Let's see what are the steps you have to do if you want to use galaxies to learn something about the dark sector. The first step to do, you have to validate your simulations. What do I mean with that? Well, when we do simulations, since we want to keep the cosmological framework, we have to sacrifice something on resolution. This means that one parcel, one element of gas in my simulation has actually the mass of 10 to the 4 solar masses. So this is not a single, practical what you would like to do if you would do the first principle, you want to simulate each hydrogen atom in the universe. Clearly you cannot do that, but you cannot do that by many orders of magnitude. That means that the best you can do is to have that your gas element has a mass of 10 to the 4 solar masses. Okay? Now what we want to create some stars of this piece of gas. And then that's when things become a bit sketchy. Because what we're going to do in our code is going to say, okay, we can't really see this particle collapse, right? This is a single element. So what we're going to say is that we're going to allow this gas to transform part of its mass into stars when its temperature is below some critical threshold and its density is above some critical threshold. So the idea is that we want cold and dense gas to form stars. When this happens, when those thresholds are satisfied, what we're going to tell our code is that, okay, now you had at the beginning one mass element, now you're going to split in two. Half of it is going to be stars, or some fraction of it is going to be stars, some fraction of it is going to stay gas. Okay, that's how we try to mimic star formation. And then another important piece of information we have to put into the code is the return of energy. Because what happens is that we know that massive stars, they tend to die, they die, and when they die, they make huge explosions as supernovae. So these explosions are going to put a lot of energy back into the system, which of course, this energy is going to go and feed back into my gas, and then which was some temperature and density is going to move as some other temperature and density. Okay, let me show all of that with a movie, because let's say pictures worth 1,000 words, so a movie is 1,000 pictures, so you do the math. So what you see here is just the gas. I'm just showing you the gas, and let's just see what happens. The gas, okay, you have to imagine that this thing is embedded in a gigantic dark matter ball. And the gas is attracted to the center due to the gravity of the dark matter. When it goes to the center, it becomes very cold, and so you see it becomes white and dense. But then when it's dense, it's going to make stars. And when stars explode, they're going to put energy back into the system. So what you see is the gas goes in, explosion, the gas goes out. You have this massive outflows. Now you see, gas was going in, again another explosion, now again it's going in, And 1, 2, 3, 4. Yeah, there you go. It explodes again, right? So this thing, usually when I talk to the general public, I call this the breathing of a galaxy, right? That's how the galaxy breathes. Oxygen, or the gas goes in and gas goes out. But now if you see the time scale, the breathing is a very long time scale, right? This is in gigayears up here. So that's how we try to simulate galaxy formation. The problem that I say is that we cannot do that from first principles. And the reason is that this is a star formation region. Okay, this is a picture from the Hubble Space Telescope. The size of this thing is 100 parsec. 1 parsec is 3 light years, just to give some dimensions. And what you see here is that new stars are forming. So these are new stars, these big blue dots. And you see this thing was embedded in some gas cloud, which is now shredded apart by radiation pressure and by the whole process of star formation. So probably the stars are pushing away the gas. And the problem is that this amazing process, it's kind of the same scale of one of my gigantic particles, right? So we cannot simulate that from first principles. So when I talk about star formation, I'm not forming single stars. What I'm trying to form is a cluster of stars, which has the same property of this one, but I cannot see the single stars. Okay?
Is that the only problem? I mean, suppose you just took a 100 parsec cubic box. There's a lot going on in here that it would still be hard to simulate, isn't there? I mean, even if you had a much finer grid.
If you're much finer grid, you can go down to, so for example, nobody's able to form a star. That's a thing, it's a fair assumption. But if you go to 100 parsec, for example, you can start looking at the actual radiation pressure, you can see the radiation transfer, you can start adding magnetic fields, a lot of physics that we cannot add, because practically all of that, it's inside my mass element, right? So I cannot see anything of this. So you can add a lot of physics if you are, but if it's very hard to have at the same time the small scales, but I also need the big scale, because I need my dark matter halo, otherwise I cannot do my cosmology. So there are other people that study galaxy formation or actually star formation, and they have boxes of 100 parsecs, okay? But they don't see the whole dynamics of them. For example, they ignore that this thing is embedded in disk, which is rotating, has some shear, and so forth. These things I have, but I cannot see the fine grid of the star formation. So all of that, as I say, it's one of my gigantic particles. So that's why we need to validate our simulation. So we have to make sure that the simulation, that the thing we do, they make reasonable guesses. And there are several relations that one can decide to use to decide if a galaxy is good or bad, because that's the thing we want to do at the end, right? We simulate a galaxy, then we ask ourselves, the galaxy we simulated, are they good or bad? And what happened here? It's my laptop is plugged in. Oh, this plug is not working?
That I don't know. There's one down there, maybe, yeah. Use the one on the wall. Does it reach?
Oh, it has to.
Well, if there's something wrong with that, let's try that one. So if these maps, you can't tell if the plug is working.
No, 91%. My laptop is fine.
Did he go to sleep?
The projector,
Yeah,
The
but
projector went off?
no, but there's nothing on the screen.
I just heard
Didn't
some
know
green
it.
light, but
It
now
was
it's
right on the glass.
I think your laptop shut down.
stopped making.
Yeah, I think my laptop decided to.
It crashed at the best possible moment.
Yeah, of course.
The smart is low at its best. Yeah, it's rebooting. Low stuff. Okay. I apologize. I don't know what happened. It's fully charged. Whatever. Thank you. What happened was during my PhD defense, I was using OpenOffice at that time because I thought it was good to have open software. And when I plugged it into the university computer, all the formula went bananas. So instead of having formulas, I have to spades and smiling faces, and so. And at the point, I didn't have any option to change it. So what I had to do just go through the talk, and it was painful at the level that. So at that point, I decided never again OpenOffice. Now I think I have to say never again. We were about here. I was saying that what we want to, this is going to come up, is to have realistic galaxies. And when we did our simulations, the relation we decided to use to calibrate our simulations is the following one. Let's go to this next slide, which is better. It's the relation between the halo mass of a galaxy and its stellar mass, okay, which is this line here. So practically you can think of that as real galaxies in the universe, they live around this line. And this is a basic property. It's practically telling me what I can form for every unit of dark matter, I can form the right unit of stars. That's the plot here is the ratio. You see that the ratio between halo mass and stellar mass is of the orders of few percent. Okay? So this relation, it's very important. It's also important because we don't only have it in observation at redshift 0, but we have through cosmic time. So we have the same relation today. That's roughly half of the life of the universe, 1/4 of the life of the universe, and so forth. So the question we had at that time was that can we tune our numbers in order to get the galaxy which is exactly on this relation on the scale of the Milky Way at redshift 0. And then we want this galaxy to evolve on this, to stay on this relation through the whole cosmic time. And we managed. It was not an easy task, but we managed to find a combination of our parameters. For example, I told you before, I have a parameter to set the threshold for star formation, a parameter for the feedback, in order to get this result. And once we got one galaxy, we decided to go ballistic, and we launched a project which is called NYU-AD, which has been the main thing I've done in the last 3 years, which stands for Numerical Investigation of 100, that's the number of simulation we wanted, astrophysical objects. And it also means hello in Chinese, and it's a collaboration between, well, where I'm now, where I was before, and our colleagues in China. And NYU-AD, this is one of our galaxies, it's 125 high-resolution galaxies. And the number is important because galaxies, they have a lot of, they're very similar to each other, but there's also a lot of scatter at the given galaxy property. For example, if you fix a given stellar mass of a galaxy, you can get extremely differences in, for example, the morphology, or the size of the galaxies, the amount of gas of the galaxies. That's why you need statistics if you want to learn anything about galaxies. Okay, this is a technical thing. This is the kind of physics we have. We have star formation. We have heavy element production, which in astrophysics, we have a very funny periodic table because our periodic table is hydrogen, helium, metals. It's three things. So I'm trying not to say that because metals means in astrophysics everything which is above helium. So argon is a metal, okay, for us. So heavy elements. Well, it's a lot of physics. And you see, we make very nice galaxies. And what was interesting is that we tune our simulations to have only galaxies. So we tune our simulation at this mass scale. If you remember, I told you we want one galaxy to stay on the relation at this specific scale, the Milky Way. But when we apply the same physics down to the whole spectrum of galaxies, all of them stay on this relation. Right? But we tune our things here, all of those, they fall on the relation, not by construction, but because it means that the physics, which is correct here, is also correct down the line. And most interesting, this thing, it's correct through redshift. So you see our galaxies are on the relation, a redshift 0, a redshift 1, a redshift 2, and a redshift 4. I mean, a redshift 4 is mainly the extrapolation of the relation because we don't have much information of small galaxies. And one can think, okay, this is very easy. You have so many knobs to tune. You can always get that. Well, actually, this is not easy. Because you might have heard of the Illustrious project. That's a big simulation project which is done at Harvard, MIT, and now also the Siemens Foundation down the road. And this is their simulations. And this is from a paper by Grant. This is the ARIPO code, which is supposed to be top-notch code. And that's the redshift 0, abundance matching. You see that galaxies tend to be above the relation. And when you go back in the past, they kind of always overshoot the relation, right? Our galaxies do quite a good job. Look at redshift 2. I mean, they overshoot the relation quite consistently. And they have the same...
Their scale looks different, and you're also high, aren't you?
Well, if you look at
let's go back. You had like...
So if you look at the scatter...
7 orders of magnitude, and they had 2.
But if you this is the scatter, right? Which color is this? Kind of slightly colorblind. This pinkish is the scatter, and that's exactly the same scatter they have here. You see they are consistently above the scatter through the simulation. And you see they are above here, and they tend to be above all the time.
So you're talking about above the curve, which I don't quite know what the curve is showing.
The curve
it's the
shown
same
is
motion.
exactly the same curve.
Right.
And
So
the
you're
scatter,
both
and the
above
scatter, you should
curve.
look at the, this is mustard, this, you should look at this pinkish
so you're
color.
both above the curve by about the same amount, but you say the scatter in yours is less?
Yes.
Because, I mean, the scale is so different, it's very hard to compare.
Yeah, that's true. But we have a lot of points that scatter below or stay around the relation, and you see they are, they are systematically above. So the point is that it's not easy because this is a highly nonlinear system. It's not that I have a knob that I can tune and get whatever I want. Okay?
Just to ask.
Yes, sure.
You do have a bunch of parameters related to metallicity, et cetera, and so on. So how much, I mean, how do you adjust those parameters? Do you adjust them to get the best possible fit on these sort of plots, or is there some?
The idea is that you pick, I mean, the idea is always the following. You pick one plot that you use for tuning. Okay? And we decide for this plot, actually we decide for this thing, we decide that we want to tune in order to have at this specific mass a redshift 0, a galaxy which is the Milky Way, which is on the relation through the whole time scale. Okay, that's what we tune for. And then we only ask for this thing to fall in place. Okay? We didn't look at anything else. So we cannot use this plot as a success of the model now because this is we tune it for. What is interesting though, that despite we tune a specific mass scale, so we tune here, so those points here, they are bound to be there, right? Because we tune it. That all those other points, and you see there are 2 orders of magnitude in halo mass, 4 orders of magnitude in stellar mass, they all fall on the relation, okay? That's not a success, but it's telling you that you are on the right track. And it's also telling me that these points, they also evolve on this relation. Okay, they don't, for example, what could happen is that the point is here, but practically it hasn't done any stars for the last 10 years, so it's always been in this point, right? When you set this point, this relation moves as a function of time. So the idea is that you use some parts as tuning, and then you look what happens to other plots, okay? Other parameters.
Does this fit your results, Jeremy, in terms of the spread?
You see, the scatter is very small.
Interesting.
Well, my constraints in the scatter are at much higher stellar masses. I think it's pretty conjecture to see what the scatter would be at lower masses. Even what the mean is actually has a lot of wiggle room because it's really hard to measure observationally.
So practically,
you say he should run higher stellar mass.
yes, we have them. Yeah, we have them now.
Yeah.
So the main reason why this plot stops here at the Milky Way is that in order to get galaxies that fit on the relation, let's say on the right, you need some extra source of feedback besides stellar feedback. People claim is AGN. And we didn't have it at that time. We have it now. I have plots towards the end if I have time to show you. Okay, since we got this very nice galaxies, we started to study them, and then we practically split our study in papers that look at the baryonic context or the galaxy formation point of view, galaxy structure, which is more the dynamical point of view, and then of course the part of the dark matter, which is the one that interests me the most. And we have written, 20 papers on Nihao in the last 4 years. This one was out last Monday. And also we have some papers on the smallest galaxy. I don't have time, neither me nor you, to go through the whole 20 papers, so I'm going to pick up only the one that talk about dark matter. But before doing that, I want to show that our galaxies are very good, for example, for some other observational relation. This is the Tolly-Fisher relation. It's a relation between the stellar mass and the rotational velocity. And here you have the Nihao galaxies, which are the black points, and the observation, which is the red one. And you see Nihao is able to get normalization, scatter, and slope of the relation very nicely. And this is not something we aim to, right? This is what I was saying before. This is not the plot we look at. For example, we can also look at the gas. So what you have here in this plot is the amount of cold gas you have. This is the size of the gaseous disk. And again, we get black is observations, red is Nihao. We get slope, 0 point, and scatter correct. And that's not something we tune our model for. Our model was tuned only just to get the right stellar mass. But practically, what's telling you with our physics, if you get the right stellar mass, you also get the right gas mass. And not only you get the right gas mass, you get the right gas distribution. Okay? Yes?
You get the radial acceleration relation?
Yes. It's one of the backup slides. If you allow me, I'll get to the end. Yes.
With small scatter or?
Smaller than observed.
Sorry?
Smaller than the one observed. Yeah. It comes out naturally from numerical simulation, from galaxy formation. I'm not sure why, but it does.
You know, I mean, it has in it some scale. Do you know where the scale is coming from?
I tried to get this answer. I think it has to do with the virial theorem and the fact that dark matter halos are self-similar, but I haven't been able to prove it. I have some thoughts, but I haven't managed to get the math to add up. Okay, now that I know my galaxies are realistic, I can try to do the reverse engineering and look at the dark sector. And the first question we ask ourselves is that it's called dark matter, the simplest model we have, a viable model for galaxy formation. And it's an interesting question because there are some problems. I'm going to talk just about one because I talked about three last time I was here, so I thought that this time I'll try to keep it short instead of showing something newer. So this is dark matter. This is dark matter view of a galaxy, and now if you look at this simulation, they only have gravity, so there's no galaxy formation. The dark matter has always this strange density profile. So this density is a function of radius. That means there is more dark matter in the center, as you can also tell from this picture. And one thing one can measure is the slope of this profile. So the rate of increase of dark matter towards the center. Let's call it alpha. Now, if you go to simulations with only dark matter, there is a slight dependence on the mass of the dark matter halo, but you see this alpha is always between minus 1.8 and minus 1.4. Okay, that's a range of alpha. That's what is predicted by the cold dark matter theory. You can measure this thing in observation through rotation curves. And now what you have here is exactly the same alpha. And this is, instead of saying a function of mass, is the points where it can measure in observations. I mean, in observations, you don't have the freedom to measure it exactly where you want. It depends how close is your galaxy, how much refined is your rotation curve. So let me zoom on this plot. What you have is that this is as a function of where you can measure the slope of the profile. That's the result. And what you see is that you have here the prediction from cold dark matter and here the data. Now, as I say, this is kind of strange plot because of the units. Forget about what's on the axis. The way to see this plot is the following. You have some place where theory produced the black line and the data are blue cloud. Okay? If I show you a plot like this, even if you don't know what the theory is, what the data is, you're going to tell me, oh, you have to adjust your theory.
Right,
Right?
but it isn't the theory, of course, because you just said it was pure cold dark matter. with
Well,
no
that's
gas.
exactly what the pure cold dark matter theory will predict you, right?
Right. But we know there's gas. So.
We know there's gas, but people always thought this was subdominant, so practically I can neglect it. But this is as
Well,
Paul.
not for years. I mean, it's been 5 years since anyone thought.
Yeah, but this has spawned tons of papers on how to modify the theory to fit the data. This goes from self-interacting dark matter. People have other models. And now, if you look, even today, if you read any alternative dark matter paper, it starts saying, well, dark matter is very successful on large scales, but on small scales has problems. Hence, we need to modify it. Okay, very easy. We can try to do the exact same plot with our simulations. Now, if the whole process of galaxy formation will do nothing, what I expect to do that when I look at my Nihao galaxies, they will somehow go around the black line. Okay? Because if galaxy formation is not able to modify the prediction of cold dark matter, that's where I expect to be my galaxy. Then I have a problem, right? My galaxy is down here, the truth is up there. But actually, what happens is that if this is the profile of a dark matter halo, when you run, which is a given slope, minus 1.3 in this case, when you run a simulation which has inside galaxy formation, so when you form this galaxy, this is the galaxy which was spinning before in the movie, that's the profile you get. So what you get in your profile is the same as in the pure dark matter simulation, but then at the end, here it gets flattened out. So practically dark matter is removed from the center and pushed outside. Now if I measure the slope, in this specific case is minus 1.14, which means that this is not what I get in my simulation. This is what I get in my simulation. So when I add galaxy formation, these points, they all move up and they start to get exactly what the theory is. So again, the way to see this plot is that now what I have is that I have data and theory with galaxy formation, that's why I call it Nihao, and the two things are overlapping. So frankly, what it's telling me is that there is no actual problem there. And one can argue, how can the baryons, which are subdominant, push away the dark matter? Dark matter doesn't interact with baryons, there's no cross-section. Well, the reason is the following, is that when you have, this is the same movie I showed you before, now I need two ends. What you see is that the gases keep going in and out, in and out, in and out, and what it's doing is making a quickly variable potential well. Okay, so the dark matter, what it sees is that the potential well is keep changing on a very quick time. So dark matter is trying to adjust to this change in the potential well. And what happens is that when the gas goes in, the dark matter goes in because there's more gravity. And when the gas goes out, the dark matter kind of moves out because now it has too much kinetic energy for the potential energy, so the orbits moves out.
But how much freedom is there in explosions that you put in? You put in explosions, right, as a feedback.
Correct.
And then you have probably a model for the explosions.
Correct.
And then that model is well understood, or there are some freedoms which...
If you give me 2 slides, I'm going to touch as how much is this model dependent. Now let's assume this is the correct model for 1 second. This is the question, right? Because practically I told you I solved a problem, but this was true only if my model is realistic, right? So when the dark matter moves in and out, what happens then when the gas goes in, it does practically on an accretion timescale. When the gas goes out, it does very, very quickly because that's an explosion. So this is a non-adiabatic process. This means the dark matter, when it goes in and goes out, it cannot go back to the same position. And kick after kick of these explosions, what happens is the dark matter moves out. Okay, that's the explanation. That's exactly what I told you last April. The question is that, is this model dependent, right? As Greg was hinting to. Well, what happened? The answer is yes. In fact, there are 2 big fields in this thing. There's a group of people that say, actually, there is no dark matter modification. So in their simulation, they don't see anything because they have different model for these explosions. And there's other groups, which is us, people in Caltech, we say, yes, there's a big modification. And that was a big problem till a few months ago, because it was very hard to compare results, because we have completely different codes, completely different assumptions for supernova explosions, and so far, so on. But lately, we've been able to boil down all this problem to just one parameter. We find out that actually, in this complicated network of how you make gas, how you do the explosion, there's only one parameter that actually matters, and it's this one: the density at which you allow stars, gas to form stars. This is the key parameter. Yes?
But it's not that the ones on the left are cosmological sized boxes and the ones on the right are zoom-in simulations.
No, because
there seems like an obvious difference between those.
No, because Auriga and Apostle are the zoom-in projects of these 2 simulations. I glanced at that because I thought it was a detail. Those are zoomed, and those are zoomed. No, the resolution is exactly the same. It's literally how you do the star formation.
And just to be clear, no dark matter modifications, you mean baryonic physics doesn't affect the dark matter distribution?
Correct, yes, that's what I meant. So practically, blah, 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 blah.
You get this.
This is what you get. No dark matter modifications means the points stay exactly as they would in, yes?
In your attributions, you had UW and Rutgers as if they were part of the Nihao group, are they?
No.
Because
The
they
reason,
were the
yeah.
ones I first learned about this stuff from.
No, in fact, they are black, but we use exactly the same code. So practically, those are not independent claims, because since we use the same code, this is University of Washington, this is Alison Brooks. We got similar results, but we use the same code, so it's not surprising we get. That's why they are.
Were you able to do a lot more simulations thanks to what's it called, Butina?
Yeah, Butina and Dharma. Yeah, that's how we ran tons of the simulation. That's why we reached 125. That's a computer in Abu Dhabi. So everything boils down to this number. So let me give you some overview. This is the density of a star formation. So the density usually is measured in atoms per cubic centimeter. And this is 100. It's where giant molecular clouds form. That's a picture I showed you before, right? This gigantic ball of gas. And actually, star formation, people think, forms around 10 to the 4, 10 to the 5 protons per cubic centimeter. Out of curiosity, do you know what the density is of the air in these units in this room? 10 to the 27. So these are very, very low densities, right? 10 to the 5 is big, but the number of molecules per cubic centimeter of iron in this room is 10 to the 27. It's Avogadro order of scale.
Saying it's 10 to the 4th times Avogadro.
Yeah.
That doesn't seem right.
10 to the 27 molecules per cubic centimeter in this room.
In a cubic centimeter of water, there's 10 to the 23. Isn't that right? Am I completely confused?
No,
10 to the 20, 10 to the 20. I apologize. 10 to the 20. It was 4 times less than Avogadro. 10 to the 20. I had it there in my notes, but I couldn't see because I had to, well, whatever. Okay, and now the 2 different groups, the one that find no modifications, they put the density threshold around those numbers, where our group, they put it between 10 and 100. And that is interesting because we managed to show that if we use the same number they used, we get exactly the same result. So everything now boils down, what is the density more correct for star formation? I'm going to skip on this. So which value of this is more correct? And we find out that observations can tell, because if I run exactly the same simulation with these two different thresholds for star formation, what happens is that if I have a very high threshold, well, you see that this is star formation rate, number of stars I form per year as a function of time. If I have a very high threshold, this thing is very spiky. And the reason is that I have to pile up a lot of gas before I can make stars. Then when I make my stars, I make a lot of them, then nothing for a while, and I do it again. Where if I use a low density threshold, this thing is much smoother. Well, the good thing is that observations can tell the difference, because what I can measure is, for example, the scatter, so the RMS in this plot versus the median, and these two things, they really separate. And for example, now we are doing projects with people that understand star formation from the point of view of observations better than me, and if you use some star formation proxies like H alpha, you can be able to measure what is the RMS of this fluctuation. Another thing you can look at is, for example, there's a project with a student, it's the clustering of stars. So this is not the same galaxies, and here you just see the young stars in this different threshold, and you can measure their two-point correlation function, and then this is the power index of the point correlation function, and then you see that if you use a high density threshold, you get this violet line, which is in agreement with what has been measured. This is some survey, and if you use a low density threshold, this thing is below the survey. So the main point here is that I don't want you to convince that we are doing better than others. What I want you to understand is that we had a very deep question. Is Calder matter a viable model for star formation? And thanks to simulation, we have been able to recast it in a very simple question, something we can observe, okay? Which is what the typical variation of the star formation on a scale of 5 megayears. And that's the power of simulation. That's how you can use this reverse engineer. If you learn about star formation, the galaxy formation, you can go back and learn something about the dark sector.
So one of the observations that already exists is there is a threshold for in surface density disks for star formation to become efficient, right? And so, but I don't remember how that can.
No, that's a
Kenika-Schmidt.
Kenika-Schmidt law, I think, what you're referring to, right?
So there's the Kenika-Schmidt law, but there's also a threshold below which the star formation becomes very inefficient.
Could you go back like 3 slides, because you had it on one of your plots, I think. Oh, sorry.
I don't know what's happening. My computer's failing me at all possible levels.
Oh, I'm sorry.
So, but you're talking this one?
It's the one now. Isn't you say that yellow
Yeah,
star
because
was
this is the 3D density. What you're talking about is 2D density,
Yes.
right?
Yeah.
It's not easy to cast one into the other, because one
Well,
is
it's
more
not
like
easy for the observers. It's easy for you.
Yeah, practically all those simulations, they all reproduce the Kenika-Schmidt law, because the Kenika-Schmidt law,
see.
it's on a scale which is average out all this. So this happens, so this is the density I need in my 100 parsec element, where what you're referring to is more like a global scale on kiloparsec, so it averages out. So you cannot use that
Okay,
threshold.
So you do reproduce those.
Yes, everybody does it.
And Auriga also.
Exactly, everybody does it.
Okay.
Because it's practically, this is on small scales. What you're talking about is a much larger scale, so there's kind of an averaging
Okay.
process.
But why don't we know just from observations of molecular clouds? I mean, I'm a little confused.
We know the problem is that nobody can go up to 10 to the 5, but this is a resolution thing. So practically what happens is that we push it as high as we can. So we try 10, 50, 100, and results converge. Those groups, for reasons that escape me, they use extremely low threshold. And the reason why, I know what reason, is that if you use this threshold, the simulation is 5 times faster. So it means that instead of lasting 2 months, it lasts a year. So we spend 3 years doing simulations, so they are cheaper, if you want.
So then you have to sort of convince yourselves or us that were you able to simulate with the higher densities, you would still get the same answer since you're agreeing now. You might worry that
exactly. What people have shown at 10, 50, 100, or 200, we converge. Now, you can only converge, you can push this game, but above 10, it's very severe results. There was a question, I raised the hand.
I was just going to ask the same thing about why. What you just explained, I was going to ask.
Okay.
But so, actually, can I ask, so, I mean,
Sure.
you have a much lower, these other simulations have a much lower threshold.
Yes.
So they produce stars much more often when the gas is much
Yes,
more
much more often
So they have
on a
many more-
larger. They produce stars all over the place in the disk of the galaxy.
No, so the
So-
effects sort of average out when
Yeah.
they're exposed.
So probably they get at the end they get the same stellar mass. So look at here. I mean, this is one of our galaxies. You see that this is the position of the new stars, and it's all across the simulation. Where if you have a high density threshold, it's all concentrated in the center at some place on the spiral arms. Okay.
So-
But at the end, the stellar mass is exactly the same. So you can use this as a diagnostic.
But the effects of the explosions are concentrated in the densest areas for
Yes.
Okay.
I kind of lost track of time because I have to restart my computer 3 times. So
We've got about 10 minutes.
10 minutes? That's more than enough. So now the next question is that how do galaxies respond if I change now the property of my dark matter? I can go a step further and say, okay, now forget about cold dark matter. I put in my model for dark matter and see what happens to my galaxies. Unfortunately, I'm going to show that this calls for even more accurate modeling of the baryonic effects. So lambda CDM is very successful on large scale and redshift 0. It means that if you want to look for difference between different models, you have to look somewhere else than large scale and redshift 0, because all models are bound to do as well as lambda CDM on large scale. So there are 2 places. You can either go high redshift, or you can go to very small scales. And I'm going to give you some examples when you change from cold dark matter to warm dark matter. But this applies to practically any alternative model of dark matter or dark energy. You have to look for differences either high redshift or small scales. The small scales, so we run this Edge of Galaxy Formation project. The idea is that we have 27 new simulations. So just to go to pictures, when you go to extremely low masses, the simulations becomes peculiar, because this is the dark matter view of an extremely low galaxy. It's a 10 to the 8 solar masses dark matter halo. But doesn't look much different to the one you saw before in the movie. But now if you look at the stars are only concentrated in the center. There's no stars in any of the big satellites. Remember before there was a satellite coming in the movie, you had its own galaxy? Here is very, very different, because you are here, as I say, at the edge of galaxy formation. So this is the kind of smallest galaxies you can form.
So what was the mass of the?
This is 10 to the 8. Few, 10 to the 8. Okay, what we did, we pick our simulations, so we rerun all of them in warm dark matter. Warm dark matter is just a model when you have some thermal velocity. In the dark matter, that means that you miss some power on small scales. And then we start looking at differences. So in those plots, you always have cold dark matter in blue and warm dark matter in red. This is again the same plot as before, stellar mass, halo mass. And now you see there's not much of a difference. Red and blue points, they stay together. One thing for experts is that you get many more dark galaxies in warm dark matter. So those are galaxies, I put them here, but didn't have any single star in them. So those are dark matter halos, so they didn't even form the little thing. And you have more of those in warm dark matter, but since we don't know how to detect them, I mean, Technomag has some ideas about stellar streams, but it's very hard to detect them. Another thing we look at is the property of the galaxy. This is the velocity dispersion of the stars in the galaxies. That's the size of the galaxy. And again, blue and red points, they occupy the same parameter space. That's pretty disappointing. This is for 3 keV warm dark matter, which is kind of the warmest. This is what is still permitted by other observations, for example, from the Lyman Alpha Forest. But then we found that in one specific plot, they start to separate. This is this one, where you have, as a function of the stellar mass of the galaxy, the average age of its stars. You have 3 lines, blue for cold, red for warm, and this black one is for the observations. And what you find, if you just look at the difference between red and blue, is that warm dark matter galaxies are on average 2 years younger than cold dark matter. That's an interesting effect, and one can hope to use it to distinguish the 2 models. The problem is that, that's exactly what I say, can we use this effect to distinguish? The problem is that we don't actually measure, when you go to a real galaxy, you don't measure the age of the stars, right? This is a number I have in my simulation because I know when each star formed. By real galaxies, what you measure, it's a spectrum and some metal heavy elements abundances. Okay? And then it's when we realize that our code, for example, was only tracing few elements. Was tracing total metallicity, Z, helium, oxygen, and iron. That's everything we were doing in the chemistry. And then unfortunately, there's a lot of other elements that bring a lot of information into the, in trying to compute the age of stars from observation. So what we realized that suddenly we have to care about chemistry, which I never did in my life. So what happens is that now we have coupled our code. So probably what I say, we outsource the chemistry. So we couple our code with another code, which is called ChemPy, who is able to compute as a function of time for different types of stars, there's AGB stars, there's supernovae, the yields of different elements, of carbon, nitrogen, iron, and you see the different things. And we can trace now practically every element in the chemistry. And that's where, for example, I found out that if you care about warm dark matter, you start to care about EU. You know what EU is? It's europium. I mean, I have no clue what europium is in the periodic table. Do you? How long does it take to find europium? It's down there, right? So suddenly I became an expert over europium. Why is europium important? Because europium is an R process element and is produced mainly in high mass stars. So it's very important to trace the feedback and the star formation. So suddenly I had to start to care about things I didn't before, and that's why I became myself an expert in europium. But that tells you that if you care about warm dark matter, because that's what I care about, you just start to care about chemistry. Okay? So that's why you have to keep improving your code until you don't have to keep up with the observations. And last thing is about the why high redshift. So I can show you this movie. This movie is the same galaxy running 4 different models for dark matter, and you cannot tell me which one is which. They all look like the same. And that's because here the simulation is after redshift 3. So it's the latest evolution of the simulation. But if I show you the exact same simulation from redshift 100, now you can tell immediately which model is which, right? This one is cold dark matter, it's evolving much faster. And then in this way you have warmish and warmish models. Okay, just to give you some numbers. So that's why you want to go high redshift, because models that look like the same today, they're very, very different at high redshift. So if I restart the movie, you will see, oops, there you go, that the model with like cold dark matter makes everything earlier. That's why also the galaxies are older. Okay? So if I go high redshift, I might hope to catch them in this stage, when I can tell them apart. So that's what we did as a project with one undergrad student at NYU Abu Dhabi. And for example, we look at the number of gases with a given stellar mass, and you see they open up here. This is 2 different models. Unfortunately, this is a bit beyond what can see. Observations mainly go to this line here, so this was a bit disappointing. But one thing we noticed is that the total number of stars formed in the simulation, so if I sum up all gases, small and big, was different. And this has an effect because you know that the universe after recombination was neutral, and today is fully ionized. And the universe is ionized by photons produced by stars. So the fact I have different number of stars might tell me something about when the universe was ionized. That's exactly what you have in this plot. This is a function of time. Here you have the fraction of neutral gas. And you see that by redshift 6, this fraction is 0. So by redshift 6, the universe is highly ionized. Now you see that in warm dark matter, since I have less galaxies, the warm dark matter takes longer to ionize and now enters in this region here, which is, let's say, forbidden by the data. Okay? And this is great. It means that I have way to separate cold dark matter from warm dark matter. So cold dark matter makes the universe ionize too late with observations. But unfortunately, this is for a specific number. So this is the number of photons that actually escape my galaxy and go to ionize the universe. And unfortunately, I can compensate this effect by just changing this number. So practically in warm dark matter, I have less stars, but I just can say that more photons escape. So this is roughly twice the escape fraction. And this will compensate the thing. And then I get this delta line. And then again, this means that if I want to use this kind of data to separate the two, I need to learn how many photons actually escape a galaxy. So again, I have to, so I get limited set of poor knowledge of complex physics, and I have then to start to learn how photons escape galaxies. So that's what we are doing now. And for example, I became interested in radiation transfer, because if I want to learn how photons escape a galaxy, I have to actually shoot photons from my galaxy, see how much of them are absorbed by gas, what's the density of the gas, how much of them get scattered, and so far so on. So bottom line is that again, if you want to use galaxies to understand dark matter, you have to improve your understanding of galaxies. But this is very good, and this is my second last slide, because actually many facilities and experiments are going to tell us a lot about the high redshift universe. This is a picture of the ALMA telescopes. This is JWST. This is supposed to be launched next year, and it's going to tell us a lot about properties of galaxies very high redshift, which I told you will bring all information about cosmology. This is a SKA, which is an experiment about reionization that might or might not happen in the next 10 years. The jury is still out. And then on the small scales, for example, Gaia. Gaia is telling us a lot about the distribution of stars on small scales. So practically the thing is not hopeless, and then I can jump straight to my conclusions. So we have to remain ahead of the competition, and that's many things we're trying to do in our simulations to try to learn more. No, I have to go like this. Yeah, that's a new project. It's called Salam. It's a large box full of galaxies, and this is the dark matter view, and this is the galaxy view. So we are creating now 35,000 galaxies. That's very important to study, for example, the distribution of galaxies as a function of the cosmological model. So conclusions. Galaxy formation can tell us if cold dark matter is alive or dead, and I think it's pretty alive. There's no big problems for cold dark matter because galaxy formation can solve all of them. And galaxy can be the key to shed light on the dark side of the universe. And since since the particle physics part of the dark matter search has been not much conclusive so far, galaxies might be maybe our best option. But you need to care stuff by European, which is very fun. Thank you very much. And somebody asked about where was the question? Acceleration, there you go. This is you asked, right, about the radial acceleration. This is the relation. This is the, yeah, I might or might not explain it, depends on what's the interest in the room, as maybe to answer your question. So we get it. It's exactly the same as the data, and the scatter is more than what they observe. Actually, I have a better plot. The scatter is 0.7,
So
0.07.
So the red line is the best fit to the data?
So the red line is the prediction from Mond, which is a very good foot. There are no observational data on this plot because I didn't want to taint it with anything just to do with reality. So this is the line which is predicted by this alternative, this modified Newtonian dynamics, and these are the results of my simulation, which are perfectly fit. So probably simulations can reproduce Mond dynamics almost perfectly.
That means that your dark matter placed in this time-dependent field created by feedback, if you integrate it out, that's going to give you Mond law.
Exactly. Exactly this means.
Oh, that's great.
It is. Which means that practically every success of Mond can be replicated by simulations. And in the paper we go into the why is that thing. We don't have a final answer, but it has to do with the fact that you cannot pack as much dark matter as you want in a galaxy because of the Wheeler theorem, you cannot squeeze dark matter. And that's, but it's very nice that it comes out. I mean, the paper is out.
Is the radial acceleration data you're talking about the stuff that I associate with Lillo and McGaw?
Exactly. Exactly.
It would have been nice to see it.
Yeah, I have. I don't know if I have here the best, but the paper is out. I mean, it's on the archive where we go on the deep. We dissect this thing in all possible ways, and we always get it. It's very interesting.
So you have no intuition where the scale where it deviates is coming from, because somehow that has to do with Hubble, right? It's the same in natural units. It's just Hubble.
No, I think that's more a coincidence. I'm not sure why it's Hubble.
But coming into the simulation somehow through that.
Yeah, the simulation gives exactly that scale, but the scale is not built in the simulation. I think what it has to do here is mainly the dark matter fraction in the gases, which starts to depart here. Why the thing is the same units of Hubble, I haven't wrapped up my head around that. It's because that's not the scale. The simulation doesn't know about the Hubble constant, because the simulation is running in comoving coordinates, so practically there's no actual expansion. So the simulation doesn't know about the Hubble constant.
So that's just a coincidence?
I think it is.
And but you don't know where it actually is coming from in the simulation?
I do not.
Why this exact value 10 to the minus 10?
I don't know. The idea, I think, it has to do with the Wheeler theorem. I think it has to be easy to prove, but I haven't been able. It has to do with the Wheeler theorem and the fact that dark matter is subsimilar. But I haven't been able to prove it, why the scale comes out. But it does come, and we didn't know about that. So this thing just happens to be. Very, very interesting. And then actually, every group gets the same. Doesn't matter which threshold you use, doesn't matter about any, every group gets this thing. So this thing is kind of meant to happen.
Yeah, so it seems to be that you've sort of shown that you need to start sort of accurately simulating baryonic processes at smaller and smaller scales in order to be able to distinguish between these different models. So I wonder if you're worried that at some point you might reach sort of a wall where the processes that you have to simulate are finer than the sort of because you showed at the start of your talk that your particles are of a certain size where they sort of agglomerate, you know.
Well, you go hand in hand. So practically,
Yeah.
the more physics you add, you also have to push down the resolution.
Right, okay.
It's doable thanks to Moore's law that makes computers better. The fact that we make code smarter. And so, but the two things have to go in hand. You cannot just keep adding physics, because at that point you're just adding epicycles inside.
Right.
Yeah, I fully agree with you. For example, it would make no sense to add any magnetic field to my simulations because I cannot resolve them on any meaningful scale. In fact, people that add magnetic field on this kind of simulation, they arrive to the conclusion they don't modify anything, which is not surprising because you don't see the magnetic fields on the region, on the spatial scale where they do actually matter.
So when you simulate these warm dark matter zoom-in simulations, do you worry about these sort of low-mass artificial halos that are floating around in?
You do. There are two ways to beat them up. One is resolution, and the other fact is that since now the limit for warm dark matter is around 3 keV, these very small halos happen on a very extremely small scales that I don't have to care much. So that's true if you use very warm candidates, like 1 keV, half of a keV, yes. At 3 keV, they are below the resolution. So somehow the limits help you not to worry about that. But you need to increase the resolution to around warm dark matter, yes.
I wanted you to elaborate about the europium because it seems like, in fact, now it's controversial whether it's supernovae or binary neutron star mergers that produce our process elements. And so you indicate, I mean, maybe you were being a little bit facetious about europium. But
Europium is
you
just more a joke because
Right.
I didn't even know it existed till a couple of years ago, more or less. I mean,
But are you wouldn't, I can't imagine that your simulations it shouldn't matter, one would hope, what was the origin of our process.
Correct.
Okay.
But the amount of europium, it's important to test our, for example, the IMF, the initial mass function we use, how many massive stars we get.
Really?
Well, that's what people tell me, that this is very important. So I haven't traced the europium yet in my simulation. I have no idea how europium is distributed, but people are making big fuss about europium because apparently it's the thing that sets many astrophysical processes. Yes. I've seen at least 10 papers in the less than a year about the europium distribution. At that given point, I say, okay, I have to give up.
Is it something like it has a real special spectral feature so that it's
Yes,
easy
it's very
see
easy
it?
to observe.
I
That's
see.
why.
So
No.
Even though it's a sort of an obscure element. It's
No, I mean, in astrophysics
identifiable.
we do what we can, right? The
Okay.
same is
No,
for
no, fine.
magnesium.
Okay.
And magnesium is very popular, and the reason is that it's in the right place of the spectrum, especially when
I
you move
see.
to high ratio. Yeah. No, europium has nothing specific around it. It's the fact you can see it, and there's this R process flavor. Yeah.
Okay, so if there's more questions, there's going to be a reception. I have no idea where it is. Is it upstairs?
Actually, are you hosting?
I have no idea.
Upstairs or next floor.
Check with Lorelai.